Natural gas coming out of the ground consists of different hydrocarbons in varying amounts. Under certain pressure and temperature conditions, some of the components of natural gas can be held in liquid state. These are known as natural gas liquids, or NGLs. In this first of two modules, we will look at natural gas liquids and devices and methods for measuring them. This is the first section of a two-section module covering natural gas liquids measurement. In this section covering NGL measurement, we'll look at some of the characteristics of NGLs and NGL measurement, as well as some of the basic components which make up a typical metering station. First, let's look at some of the characteristics of NGL flow. As NGLs flow through a pipe, they exert a constant pressure against the walls of the pipe known as static pressure. When a constriction is placed in the pipe, it causes the velocity of the NGLs to increase. As the constriction reduces the area through which the NGLs pass, the speed or velocity of the NGLs increases to maintain the flow rate. When the velocity increases, the static pressure decreases. This pressure drop, known as differential pressure, is the difference between upstream static pressure and downstream static pressure. Changes in the flow do not always create desirable effects. Undesirable changes include fluid pulsation, or uneven flow, which can be created by cycling sources. Rotational flow, a swirling, which can be created by obstructions in the pipe. Fluid running faster along one side of the pipe than on the other, caused as fluid exits bends and elbows in the piping system. While some desirable flow changes can aid in accurate measurement, undesirable changes reduce accuracy. To measure and record the flow of NGLs, a meter station is used. Now, regardless of the metering device, the meter station consists of a primary element with associated components and a secondary element. Typically, the primary element includes a meter tube, flange union, and a metering device. Associated components may include strainers, static mixers, straightening vanes, thermal wells, back pressure regulators, check valves, isolation valves, vent valves, and sample probes. The secondary element includes piping, recording device, density meter, sampling recorder, and mixing device. Let's take a moment now to look at each of the components in a little more detail. The meter tube is a straight section of pipe on the upstream and downstream sides of the metering device. For accurate measurement, the tube must deliver NGLs to and past the metering device with minimal turbulence. The volume of liquid flowing past a point in the meter tube is measured by a metering device. This device is usually joined to the meter tube with a flange union. Basically, there are two types of meters for NGL streams: inferential and volumetric. An inferential meter measures liquid flow not as volume or weight, but as a function of some action from which the quantity of fluid can be inferred. Now, the action observed is either pressure differential or velocity. Common inferential meters are the orifice plate and turbine meters. Volumetric meters, more commonly known as positive displacement meters, provide a continuous method for measuring NGLs. The quantity measured depends on the number and size of passages and motion associated with each meter. Typical meters of this type are the rotary sliding vane and oval gear. A more detailed explanation of each of these meters will be included in NGL Measurement 2. Several components located on a meter run are not considered part of the primary element. They are, however, important in the accurate measurement of NGLs. The meter stations at your location may have all or some of the following associated components. Thermal well. The thermal well provides a location where the temperature of the NGLs can be measured. Thermal wells are usually located downstream of the metering device, as they can create unwanted turbulence. Back pressure regulator. A back pressure regulator maintains a predetermined minimum pressure in the meter tube by regulating uneven flow pressures. Check valve. If the pressure downstream of the meter tube becomes greater than the pressure in the meter tube, check valves prevent backflow of NGLs. Isolation valve. Isolation valves provide a way to isolate the meter tube from upstream and downstream line pressures. Vent valve. Vent valves allow the meter tube to be depressurized after it has been isolated from upstream and downstream line pressures. Sample probes. Sample probes provide a location for collecting NGL samples while the meter tube is under pressure. A sample probe is inserted into the meter tube, usually downstream of the metering device because it can cause turbulence. The probe is never used as a vent valve. Strainers. Strainers eliminate the solid particles in the NGL stream before they reach the metering device. Two other associated elements, which may be present on the meter run but not seen, are straightening vanes and static mixers. Straightening vanes are inserted into the upstream part of the meter tube when the meter run is not long enough to eliminate turbulence. Straightening vanes eliminate swirls, rotational flow, and cross currents resulting from pipe fittings and valves. Since NGL sampling requires the product stream to be well mixed, a static mixer is installed upstream of the sample probe. Now let's talk a moment about the secondary element. Typically, the meter tube is connected to the recording device with piping. Other piping may connect the meter tube to a density meter or sampling device. This piping supplies line pressure data to the different recording devices. A recording device is found on all meter runs. This device records volumes digitally and on charts for sales and purchase records. A densitometer records the density or mass per unit volume. The gravitometer records the liquid-specific gravity, which later can be converted to density using the density of water at specified conditions. Most NGL runs will have a densitometer or gravitometer. Samples should be taken continuously from an NGL stream. The sampler is then a part of the secondary element. A continuous sampler takes samples at intervals from the meter tube. One word of caution, however, since NGLs tend to layer over time, a mixing device should be used to mix the NGLs before taking a lab sample. One final piece of equipment which might be included on an NGL line is a recorder. A recorder, which is part of the secondary element, can be used to record volume, flow, temperature, pressure, density, and time of sampling. This concludes the first section of our module covering natural gas liquids. Take a moment now to look over your student manual. View this tape again if necessary, and answer the questions after section 1. In our next section, we will look at how some of this equipment is used for NGL measurement. In our last section, we saw some of the basic components which make up an NGL metering station. In this section, we will look at how this equipment is used. We will also look at some of the methods used for NGL measurement and at some of the factors which affect measurement accuracy. This is the second section of a two-section module dealing with natural gas liquids measurement. Measuring NGLs involve correctly reading instruments and making appropriate calculations based on these readings. Different measurements for NGLs include volume-only measurement, mass measurement, and component measurement. For pure single-component NGL streams and NGL streams with less than 10% ethane, volume-only measurement is acceptable. However, whenever the NGL stream has temperature and pressure variations, molecular nesting, or solution mixing problems, then mass measurement is highly recommended. To better explain the difference between volume only and mass measurement, let's look at an example.
Now let's suppose you have two barrels, a barrel of basketballs and a barrel of golf balls. If you empty these two barrels into a two-barrel container, you'll find, because the small golf balls fill the spaces between the basketballs, you'd have less than 2 barrels of combined balls by volume. But if you weighed each barrel separately, you'd find they weighed the same. Now this characteristic is known as non-ideal mixing or molecular nesting. The same thing happens with ethane in the NGL stream. To correct this measurement problem, mass measurement is used.
Now let's look at each of these methods in more detail, starting with volume-only measurement. NGL volume can be measured by inferential or volumetric meters. Inferential measurement utilizes either an orifice meter or a turbine meter. Volumetric measurement is taken with a positive displacement meter.
With the orifice meter, the orifice plate creates a pressure drop. The differential pressure is recorded on a chart. Many times the static pressure is also recorded. This chart, when integrated and combined with the meter factor, meter correction constant, temperature, and pressure correction, provides the NGL volume. The turbine meter measures volume using the rotation of a rotor. As fluid flows across the rotor blades, they spin in proportion to the volume flow. Volume of flow is given by combining the rotor speed with the revolutions per unit of volume.
Our final volume measurement device, the positive displacement meter, directly measures volume.
Using dividers, a known volume is separated from the stream, counted, and then returned to the stream. The volume is determined by adding the known revolutions with the number of volumes counted.
In instances where ethane is 10% or more of the NGL stream, or where the stream is mixed, the mass measurement method is used. Mass measurement is a simple concept in which you measure the gross volume and density of the stream. These quantities are multiplied together to give weight or mass. If we know the average weight and percentage of each component in the stream, we can calculate the exact volume of each component.
Component measurement relies on sampling of the NGL stream. This sampling assures the quality or composition of the product stream. Usually this sampling is done with a continuous sampler. For a more detailed explanation of the sampling methods used, review the information covering NGL sampling in the module Natural Gas and NGL Sampling.
Today, a whole industry has developed around NGLs. Because of their importance as a revenue producer, every effort must be made to accurately measure their volume. However, numerous factors can affect the accuracy of NGL measurement.
First, solid particles can damage any of the volume measuring devices. Solids can break parts off meters, can upset the movement of meters, and can pit parts of the meters. Usually a strainer is installed upstream of the metering device to remove these solids. A second factor is flashing of the product. In any NGL measurement, the pressure must remain above the minimum pressure and below the maximum temperature of the product being measured. If there is any deviation, flashing occurs. Flashing causes meters to spin inaccurately, densitometers to register incorrectly, and samplers to sample the stream incorrectly. A back pressure regulator and valve set for pressure well above the bubble point of the liquid can control this problem. Pulsation can also be a factor in metering accuracy. Pulsation can be caused by metering stations too close to pumps, or through inadequate control of the upstream flow. Dampeners can be used to reduce the problem of pulsation.
A fourth factor is contact with caustic, amine, and glycols, and affects primarily the mechanical meters. The best way to prevent problems with these substances is to remove them from the NGLs and carefully check and maintain meters. Other factors affecting accurate NGL measurement include pressure differences between measuring devices, rangeability of various metering devices, viscosity of the fluid, and upstream turbulence. Well, this concludes our first module on natural gas liquids measurement. In it, you've seen some of the characteristics of natural gas liquid measurement and a typical metering station and its components. You also saw some of the typical types of NGL metering devices. Finally, we looked at some of the methods used for measuring NGLs and some of the factors affecting those measurements. Take a moment to review this section in your student manual. Preview the tape again if necessary, and answer the questions at the end of the section. Now in our next module, we'll look in more detail at natural gas liquid measurements. See you then. In the first module, covering natural gas liquids measurement, you were introduced to NGLs and NGL measurement. You also learned about some of the problems that can affect NGL measurement accuracy. Now in this second module, dealing with NGL measurement, we'll take a closer look at NGL metering devices. We'll also look at some of the basic principles and steps involved in proving or witnessing a NGL meter.
This is the first section of a two-section module dealing with natural gas liquids measurement.
As mentioned in Module 1 of NGL measurement, natural gas liquids are an important part of our revenues. Measurement of these liquids is very important. Now in this section, we'll look at some of the meters used to measure NGL volume. These meters are classified as volumetric or inferential. And we'll also look at some of the methods for measuring the density of NGLs. To measure the volume of NGLs, orifice, turbine, or positive displacement meters are commonly used. So let's take a moment now to talk about each in a little more detail. Starting with orifice meters, like this one.
The orifice meter is one of the oldest types of inferential meters. The term inferential refers to the fact that the volume is determined from some activity associated with NGL flow. For instance, to determine the volume of NGLs with an orifice meter, the temperature, orifice meter, differential pressure, and static pressure or static constant must be known. The orifice meter station creates a differential pressure and records the differential pressure and sometimes the static pressure. For a more detailed discussion on orifice meter stations, review the tape on orifice meter station fundamentals.
Another inferential meter is the liquid turbine meter. Now the liquid turbine meter is an inferential device which measures flow rate in the meter tube. It functions by sensing velocity of fluid passing through a known cross-section of the meter tube.
As the fluid passes through the meter housing, it causes the rotor to spin. The speed of the rotor is directly proportional to the velocity of the fluid. Because this velocity is determined by the volume of fluid, rotor speed can be used to calculate volume flow. Turbine meter construction is relatively simple. The meter itself is installed directly in the meter tube. The meter is a precisely balanced, free-running rotor mounted in a cylindrical housing, similar to a flanged pipe. This unit is mounted on the pipe center line. A magnetic pickup assembly is positioned as close to the rotor as possible but does not penetrate the housing. As liquid passes through the meter, it causes the rotor to rotate. The rotor blades pass through the magnetic field of the pickup and generate a pulse in the pickup coil assembly. Each pulse represents a distinct unit of volume. Added over time, the total pulses represent the total volume metered. The turbine rotor is mounted on a shaft by an up and downstream hanger assembly. Although these hangers might resemble straightening vanes, they do not perform this function. The turbine rotor blades are set at a predetermined angle. This angle relates the flowing stream, angular velocity of the rotor, and the frequency of the meter. The rotor rotates on the center line shaft by means of a bearing. This bearing is either lubricated by the meter fluid itself or permanently sealed. However, to minimize the load on the bearing, the rotor also floats. Now, this floating occurs as liquid entering the meter is deflected outward by an upstream cone which increases its velocity and causes a slight pressure drop. After passing the turbine blades, the flow is redistributed. Because the rotor hub is larger than the upstream cone, some of the fluid flows directly over the hub. The rotor then floats in balance between the upstream cone and the downstream cone. The magnetic pickup assembly is mounted on the exterior of the meter housing and counts the rotor blades as they pass. The blade tips of the rotor are made from or contain magnetic material. This material creates pulses in the pickup coil as the blades pass. These counts, or pulses, represent a unit of volume.
So far we've talked about inferential meters. Let's look now at a volumetric measurement device, the positive displacement meter.
This meter continuously divides the flowing stream into known volume segments. The segments are isolated momentarily, counted, and then returned to the stream.
There are numerous types of positive displacement meters. They include the piston, rotating disc, rotary sliding vane, oscillating piston, rotary bucket, screw and spinal vane.
Commonly used meters are the rotating sliding vane and the oval gear. The positive displacement meter consists of an external housing, an internal measuring unit, and a counter drive train. Let's look at each of these in more detail. The external housing is a pressure vessel with an inlet and outlet for connecting the meter to the tube. Depending on their pressure rating, these meters may be of single or double case construction. In single case construction, the external housing serves as a pressure vessel and as the outer wall of the measuring unit. With double case construction, the external housing serves only as a pressure vessel. Inside the housing is the precision measuring unit, made up of the measuring chamber and the displacement mechanism. The counter drive train transmits the internal motion of the measuring unit into a usable output signal. This train may be a mechanical gear train, a magnetic drive coupling, a contact closure, differential inductance pickoff, or a combination of the above.
Now that we've seen the basic components of the positive displacement meter, let's look at two meters, the rotary sliding vane and the oval gear.
The rotary sliding vane meter consists of a single or double case housing, a cylindrical rotor which revolves on a ball bearing around a central shaft, and a stationary cam. The rotor has 4 or 6 evenly spaced slots which provide guides for the blades. As liquid flows through the inlet against the extended blade, the rotor and blades revolve. This rotation around the fixed cam causes the blades to move in and out as the blade rollers follow the contour of the cam. The blade nearest the inlet moves outwardly toward the chamber wall and is fully extended at the beginning of the measuring chamber. As the preceding blade is also extended, a precise measuring volume is formed between the two blades, the rotor wall, chamber wall, and top and bottom covers. For each rotor revolution, 4 or 6 of these measured volumes are produced. A small pressure drop causes the rotor and blades to rotate, while a liquid seal between the blades and the chamber wall assures separation of the measured volume. This type of meter maintains a continuous flow of uniform velocity. The oval gear displacement meter also divides the fluid into measurable volumes. As liquid enters the inlet, one oval gear begins to isolate a volume, while the other releases its volume. As the gears rotate, one rotating clockwise and the other counterclockwise, a precise volume is measured. The density of an NGL stream is determined by use of a gravitometer, or more typically, a densitometer. The densitometer measures weight per unit of volume as compared to water weighed in a vacuum. If a gravitometer is used, it records a specific gravity of the liquid stream, and then the reading is converted to density by multiplying by the weight mass of water per unit of volume in a vacuum at 60 degrees Fahrenheit. There are basically 3 types of densitometers: the insertion or inline types, slipstream or strip sampler type, and the non-intrusive type. Densitometers can also be characterized by measurement method. All insertion densitometers are the vibrating type, while slipstream densitometers can be either balance beam, buoyancy, or the vibrating type. The vibrating densitometer utilizes the vibration momentum principle. A sample of the liquid stream flows into the densitometer. The densitometer is vibrating at one of its natural frequencies, which is proportional to its mass per unit length. Because this vibration is also proportional to the density of the liquid in the densitometer, the density of the liquid can be calculated from the vibration frequency. The slipstream densitometer requires a pressure drop for liquid to flow through it. Commonly, an orifice plate is specially installed to create the pressure drop for the densitometer. Another device used to create flow through the densitometer is a pump in the slipstream. Densitometers can be installed at several points on the meter run. However, the primary concern is that density is measured at flowing conditions, the same as those of the volume measurement. An insertion type densitometer can be located either up or downstream of the metering device. However, because its insertion creates turbulence, the densitometer should be placed some distance from the meter. All piping for slipstream densitometers should be insulated to keep the temperature the same as that of the flowing stream. The accuracy of densitometers is dependent on several factors. These factors include that the insertion type obtains liquid that is from the middle third of the meter tube, that the slipstream type has large enough piping to allow sufficient flow through the densitometer. The product is in single-phase condition, and any solid matter in the liquid is minimized. This concludes this first section covering NGL measurement meters. Take a moment now to review the material in your student manual. Preview this tape again if needed, and answer the questions at the end of the section. In our next section, we'll cover meter proving.